in class yesterday, we did an investigation. If you watched the very short video introduction on that, we did an investigation of the 12 basic functions. And that was on that white worksheet that says 12 basic functions at the top. That was really the only homework because there wasn't a way to finish that in class. There are 4 of these 12 basic functions that I think you're going to feel are like totally brand new to you. But the rest of them, you should have seen them at some point. Again, knowing what happened last spring, that's kind of iffy. It's a maybe on a couple of these. You maybe didn't spend a lot of time on them. But the 12 basic functions are, well, like it says, they're the ones we have to know. I mean, they're basic curves, basic lines, all of those good things. So our objective is really, what we want to have happen is that when I say y equals the natural log of x, that in your head you can visualize what that graph looks like, and then just give us the basic analysis of that graph. We're not asking for, individual perfect points on it. What we want to know is, can you picture what it looks like? And then go through an analysis of the graph. And analysis is bringing together all the things that we've learned about with graphs, domain and range and continuity and maxima and minima and end behavior and all of that stuff. So for this test, it's not like we want you to be able to perfectly graph each one of these graphs for us. We want to ask you some general questions about them and see if you can picture in your head, okay, this is what that looks like. And we're not taking your calculators away from you, so if you had to, you can punch them into the calculator and take a peek at them. But we already know that graph or error leaves some important things out. So there are certain things we have to know about these. We want to recognize them. What do they look like? Get that picture in your head. Determine the properties of the 12 basic functions. Well, these properties are what we call analyze. All of this right here is analyze. So from now on, instead of saying determine all the properties of the 12 basic functions, your problems will say, here is a function, analyze. And this is all the stuff that you'll be expected to do. Domain and range, continuity, intervals where it's increasing, decreasing, or constant, boundedness, local extrema, symmetry, asymptotes, and behavior. All of those things are included in an analysis of a graph. And then this little piece here that we'll start to get into today, and that's how do we combine those 12 functions in various ways to create new functions. So before I actually get into the material here, I had a little note to myself to remind you. We had worksheets in this chapter, and I'll be so grateful when we're done with all the sections where we have worksheets because people forget to submit them. So you need to check your Schoology comments every once in a while. Take a peek. Does it say, oh, you forgot to put the blue worksheet in here with this, you forgot to put the yellow worksheet in with this? I don't want to see you not get points for something just because you forgot to submit a little worksheet with it. So that was my little reminder to everybody today. As 1-3 is going to be the last section we're going to do before we're going to stop and take a test. So combining these 12 functions will be, like I said, another objective here. And usually what we were able to do for this was to get everybody in groups and have them work on, the 12 basic functions and go through all of that. You might want to have that out today. I think that might be helpful as we talk about those 12 basic functions, having that worksheet out that you worked on yesterday. Now, here's the part where I get kind of mad at the book for not doing the arrow thing, and I understand that they're just trying to take snapshots of the graph. But it really is important that we know which of these require arrows and which ones don't. So I already added them up here. You can see the line y equals x because remember, f of x is just notation, fancy notation to say this is a function. It's the output, which would be y. So the line y equals x is that perfect diagonal through first and third quadrant, and of course it goes on forever. It's a line. And then for y equals x squared over there, or f of x equals x squared, that one again you studied in great length in exponential algebra, looking at parabolas, and yes, we know that that goes forever too. It's got a domain of all real numbers, and it goes forever. And then the cubing function, same thing, we can cube any number. And we can see that that's going to go on forever. The reciprocal function, now that's one that has some unique stuff, because this one has division. And whenever we have division, we have to say we can't use 0. So the line x equals 0 actually becomes a vertical asymptote for that graph. And we found out by studying these that y equals 0 is going to be a horizontal asymptote for that graph. So that has arrows. This one doesn't. This one only gets one arrow. And that's because we know that if we try to take the square root of a negative number, that we go into imaginaries, and we are not graphing imaginaries right now. We're graphing real examples. So starts at 0, goes on forever to the right. Exponential function, that one gets 2 arrows. That one goes on forever. This is another one that can be a little bit tricky, and that's because if we graph the natural log of x on our graphing calculator, it looks like the graph stops going down. It doesn't. The asymptote here is x equals 0, and it's approaching it, but it's never quite going to get there. That's something we can't make out on the graphing calculator, so we have to know there actually is an arrow on both ends of the natural logarithm. Studied absolute value. In fact, we're doing that right now again in Algebra 2. We learned how to graph them in one chapter, and now we're talking about the inequalities with absolute values, so those go on forever. Cosine and sine, even though they're built on radians, numbers involving pi, they still do travel forever along the x, so we've got our little arrows there to show that. And these two, people are like, how am I supposed to know which one of these is which? The big difference for us right now when we're looking at these is going to be that the sine function starts right here at 0, 0. If you think of it as starting the graph right there, whereas cosine starts up here at 0, 1. And that's going to make a difference for symmetry. And so that's one of the things that we have to notice about sine and cosine. The greatest integer function, that's the one that I spent some time talking about on the video, because it is so different from anything we've ever seen before. And again, this book chooses to use what the graphing calculator has in there, which is int of x. And yesterday when I was talking to the students, I thought, I wonder why they don't use gint. I mean, is that a bad word somewhere or something? And in fact, I went and looked it up later. It's not that it's a bad word, it's that it's actually used in geothermal engineering. And so they can't use GINT on the graphing calculator because it's already been used somewhere else before. So this one, again, in the olden days, just looked like double absolute value bars. And then a couple of books decided, let's make this look like a little box here, like so. And you'll see it lots of different ways. I saw a textbook that just did the square brackets, and we were supposed to know that that's the greatest integer function. So lots of different ways that we can see it. But what this really gets to is the fact that this is the most basic step function out there. And what we want to do is be able to represent just about every situation possible with the graphs that we see here. And we were missing something, because if you talk about parking fees, that is a basic step function. As soon as you go in the ramp, you pay $3 for 1 hour. So it's a constant of $3. And then the instant that you're there for a little bit more than 1 hour, it jumps up, and then you have a new price. And so we have to be able to graph those to show people, hey, this is what's happening visually. And then we have this interesting one over here, which is called the logistic function. Logistics is basically the study of populations. And there have been a lot of studies about populations. Some of the ones that they've really taken information from involved really small islands off of Japan, that they would do things like they would take a female and a male rabbit and they would put them on the island, and then they would watch and see what happens to the population, because they're biological and they're going to have babies. That's what rabbits do. And then those babies have babies, and those babies have babies. But eventually, the population will start to die off. That's why this does not continue going up forever, because they'll starve. There's not enough food anymore. They'll start having diseases, all of those types of things. So this is really a very, very good representation of what happens to populations over time. And that's why we need that one in there. So, like I said, we have some that have arrows. Most of them have arrows on both ends. But then the greatest integer function, no arrows. And the square root function, just one arrow. And that's important. The arrows are important to what we're doing. So we have to add those on there even though the book doesn't have them in there. So now, quick reminder since you weren't here yesterday of what the greatest integer function is. I don't think this ever made it in here. No, didn't make it in your packet. The name kind of bugs me because it says greatest integer function when it's really about less than or equal to, and that's what it is. You know, we're supposed to be thinking about rounding down to the nearest integer. So that's where that step function comes from, is that thinking about, okay, I have this number 2.1, and what integer would be less than or equal to 2.1? Well, it's 2. So I would have to graph 2 as my y value. So now is why I wanted you to pull out those little white worksheets that you had from yesterday, because what we want to do is we just want to talk about what would some basic questions look like on the test about this stuff. And again, it's about recognizing it. That's part of our objective, and then figuring out what's going to fit this. So this one says 9 of the functions have the domain, the set of all real numbers. Well, I was just talking about that, about how they have the arrows, you know, and they go forever. But there's 3 that don't. So what you'd want to do is go through and see, well, which of these can't I use all x's for? And I can't help it. The first one I think about is the reciprocal function. Because you can't use 0. I mean, we can't divide by 0. That's a really big deal in math. And then I think, okay, so other ones where I couldn't necessarily use all the x's. Oh, square root. You can't put negatives in there, or you're graphing imaginary stuff. And then, were there any other graphs that didn't let us use all the x's besides these 2? Take a peek. One more that doesn't use all the x's. Did you see it? Yeah, it's that one that I said is a little bit tougher because maybe you haven't had a lot of experience with it, but you did do graphs of the natural log of x. So that doesn't go into those negatives again. So I started thinking, well, why? I mean, I want to know why. Well, that's because this really says y equals logarithm base e of x. And we use this process, the fancy name for it is exponentiation. But really what we do is we make a snail shell to read this exponentially. And what that tells me is, if I want to understand it as an exponent, that says e to the y equals x. So when I look at that, I think, well, that makes sense. Because if I have to raise it to the y, there's nothing I can raise it to that's ever going to make it negative. That can't happen, because e is a number. And if I raise that positive number to a power, I'm going to get a positive number back. So then it just starts to make a little bit of sense. Whereas normally with natural log of x, we're just trying to figure out, okay, what's this thing doing again? Now b says one of the functions has the domain, the set of all real numbers except 0. Which one is it? You're overthinking. Take a look at the 3 I have up there. Which of those can't we use 0 for? Yeah, 1 over x, the reciprocal function. Can't use it. Why can't we use it? Can't divide by 0. So the first one was talking about which of these has restricted domains. And then B follows up and says, okay, well, one of those you can't use 0 for. Which one is it? And we can't divide by 0. C says, which two functions have no negative numbers in their domains? And then of these two, which one would be defined at 0? So, which two, no negative numbers? Find one. Tell me one. Square root? Yeah. No negatives in there. What other one? I guess I'm going to have to go to Colin on you this morning. Tristan, did you find it? Yeah. We just talked about how these are the three that have the restricted domains. Of those two, which could we actually put a 0 in for and get an answer? What's the square root of 0? 0. This one. Defined at 0. So we can do that. All right, now, the next group of questions here says, let's look for continuity. 2 of the 12 functions have points of discontinuity. So they jump, they have asymptotes, they have something, so that we can't put the pencil down and draw the entire graph. Find those 2, please. Graphs with breaks, jumps. Savannah, did you find one? Oh yeah, chock full of jumps. Lots and lots of jumps. One more. Sydney, you got another one? Which one? Yeah, R0. Now they ask kind of a strange question. Are these points in the domain of the function? So they're asking us, if we were to write these, would we have told people that they weren't good x's? Well, yeah, definitely we would tell people you can't use 0 in here. So were they in the domain of the function? No. They're not in the domain of the function. I mean, we would tell people you can't divide by 0. For the greatest integer function, are those points in the domain of the function? Well, yeah, we can put all the numbers in for x that we want. We're just not going to get all the y's back. So the reason that this one is a mess is because it is a discontinuous graph. There's jumps at every integer. So this is actually a big deal. I know it looks like it's not up there. But when they ask us, are those points actually in the domain? What we always try to do when we get to calculus is use continuous graphs. To do that, sometimes we have to restrict the domain and tell people, okay, you know what, this is going to work for everything but 0. You know, we'll restrict the domain, and that way we can do calculus on this problem. So being in the domain of the function is actually a huge deal when we get to calculus. So that was about continuity. This one says, let's talk about boundedness. Only 3 of the 12 basic functions are bounded. Remember, bounded means both above and below. There's 3 of them. Which 3? Write them down, and I'll wander so I won't feel bad about calling on you guys, because it makes me think maybe you didn't find them, and that's why you're not saying anything. Bounded above and below. Lindsay, can you give me as many as you found so far? Which ones? Not bounded above. Remember, the arrows are showing us that it's going up. Okay, so you didn't have... Look again, anything that has a cutoff above and a cutoff below. It's never going to go lower, it's never going to go higher. Natalie, can you help out? Did you find one? Cosine, yep. Cosine. 1 is the top, -1 is the bottom. So then, Claire, does that help you find another one? Yeah, the sine. Yeah, cosine and sine. Okay, Lindsay, so I want to come back to you now. Do you see where cosine and sine, they max out, and then they have a lowest point? We've got one more. In fact, I think they drew it with some dashed lines, so we could kind of see where those cutoffs were. Sydney, can you help out? Did you find it? It is, it's that weird logistic function. Yeah, it's that one. Because that one does have a lowest point. Remember, that one's about populations? 0. I mean, you can't really start a population with 0, but it does have 0 as an asymptote. And you have to start off with, well, there are something, I guess there's some frogs in South America that can be both male and female and produce offspring. So you have to have one of something. So there's our little logistic right there. So cutoffs above and below, those are our bounded. Example 4 switches it up and says, let's start thinking symmetry. So 3 of the 12 basic functions are even. All right, so even. That means that they would fold over the y-axis and get exactly the same thing on both sides. So take a peek. See if you can find them. Folded over the y-axis. Josiah, you look like you already got them. What you got? Oh, the line y equals x. Folded over the y-axis, though, Josiah. Squaring function, good. Yeah, our parabola. Tristan, you look like you're done too. Did you find another one? Yeah, cosine. Not sine, cosine, because that's the one that starts up at 0, 1. One more. Sydney, you're looking done too. Absolute value function. Yep, the big V. The big V. So those would be our evens. So, like I said, we're not asking you to know, every little teeny detail about the graphs. What we're doing is saying, try to get a visual of all of these. And some people will worry. They're like, oh my gosh, so I have to memorize all 12 of those graphs? No, that list will be on the test. You'll see the list of them. But when you see x squared, in your mind, you should see that big parabola. When you see cosine of x, you should see that nice wavy curve. And you should see it starting at 0, 1. And then for absolute value of x, you should see that big V in your head and be able to say, okay, these are the things that this has. So that analysis was a really good start. This is the type of thing you'll be asked. So, analyzing functions graphically. All of those things that we said, hey, we've got spots for these on our little white worksheet. Domain, range, continuity, increasing, decreasing, constant, boundedness, symmetry, etc., etc. That is the analysis, and that's a big objective here. So this one says we want to graph the function y equals, and then we have the quantity x minus 2 squared, and answer the following questions. And I realized, well, that's not one of my 12 basic functions, but it's pretty doggone close. It has that little transformation that we've studied about parabolas, about quadratics. So this has a squared term, makes it a quadratic, and I realize, oh yeah, x. Everything that happens with x is always the opposite. So if it says x minus 2, it was actually 2 to the right. So this is a parabola that has been moved. Oh, I'm a little off there. There we go. It's a little better. 2 units to the right. Now, if I couldn't see that, if I, just went blank for a second and couldn't do that, I've still got a graphing calculator. But hopefully we can look at that and say, okay, yep, that makes perfect sense. So then they start asking us those questions about the analysis. So on what interval is the function increasing? And I remember that has to do with what's the graph doing from left to right. Well, that's not this part because that's decreasing. But right here, that's where it starts increasing. So my increasing is going to be from 2, because I use the x's to describe that, to the right forever. 2 to infinity. And then while I'm at it, they say, okay, well, now go back to decreasing. Okay, well, that was the rest of the graph. So as we came in from the left, negative infinity to 2. So there's the increasing and decreasing, which would all be parts of the analysis. B says, we looking at odd, even, or neither? What do you think? Does it have symmetry with the y-axis? Is it even? If we take this and go 180 degrees about the origin, would we get it back? Not the exact same figure. So this one is neither. Neither or neither. Does the function have any extrema? So a highest point or a lowest point? Well, we can't say a highest point. We've got arrows. We can see that going. But yeah, it has a lowest point. So it is a local minimum. But in fact, with this graph, it's also the absolute minimum. It has a lowest point. So local minimum and absolute minimum of blank at x equals blank, because that's how we always write the extrema. The focus is on the y's. So what's the lowest y value this is going to get to? Natalie, lowest y value? 0. It's this point right here. There's our lowest y value. And it's pretty obvious it's going to happen at 2. So it is a local minimum. If somebody said, you know, just look at this area of x's here between 0 to 4, you know, is there a local minimum? Yes, but it is also the overall lowest point of the graph. So that is our absolute minimum. D says, how does the graph relate to the graph of that basic function y equals x squared? That's what we want to be able to do. We want to look at it and say, this was x squared, but they did something to it. And what they did was they translated the graph 2 units to the right. Now, there are certain things that when you're taking your AP exams, again, we don't do that in this course, but when you get to calculus, that we call brownie points. They like to know that you know the correct vocabulary. We could have just said they shifted the graph 2 units to the right, but that's not the correct wording when we talk about all of our geometry transformations. If you use translated, that helps somebody, the person that's scoring your paper, to say, this person really knows what they're doing. I mean, they're even using the correct vocabulary as they talk me through what's going on. So we definitely want to use that correct vocabulary as we go through things this year. Now this one's interesting. This one brings us to the third big chunk of our objective, which was combine the 12 functions in various ways to create new functions. This is huge in computer programming. Computers speak math. That's how you program a computer, is by using math. So I'd look at this and I'd think, all right, I could chunk this up into 3 pieces. I could use a line for here to here, here to here, and here to here. But the best way to do it is to use as few pieces as possible. So I start thinking, I've got some Charlie Brown looking V's here. I wonder if I could use an absolute value for one of these, if that would take care of this. Well, absolute value has to be symmetric. So I'm looking at leaving this portion, and I know people that are looking at the video can't see that, just this portion, and I'm asking myself, is that symmetric? And the answer is no. That's not symmetric. So I can't use an absolute value for that portion. So maybe I better try leaving this off and take a peek at that one and see, does that look symmetric? Yeah. The line x equals -2 will be right in half there. So I should be able to do this with 2 pieces. I'm going to call it f of x. And then the first thing I'm going to do is I'm going to section this off, x's. This was my absolute value portion that I wanted here, and I notice that I've got 0 and then it'll go to the left forever. So I'm going to use x and 0. Now here's the next thing I think of. Should I put an equals bar there or not? Well, as it turns out with this one, it's not going to matter as long as we put an equals bar somewhere. It doesn't matter, and that's because these points actually hooked up together. So I'll just get it out of the way now and say less than or equal to. Oh, I know I didn't leave myself enough room there to write my absolute value. So x is less than or equal to 0. Now, if that's absolute value using AH and K is definitely the way to go. So let's see. H and K are the vertex. Well, that's up here at negative 2, 2. So I already have 2 out of the 3 numbers that I know I need, because that's H and K. The other thing I need is A, and A is the slope of the right side. Now, this part may make you a little nervous, because you're thinking, oh my goodness, are they going to ask us to know all of that about like the logistic graph and all that kind of stuff? No, this was last year's material, and exponential material is going to show up today. We won't ask you to put together a whole bunch of new things that you haven't had a lot of experience with. So with this one, it's, hey, we're studying this right now in Algebra 2. I can tell you, you did this last year. You did. So the slope of the right side of the graph, I'd use these 2 nice grid points and say to go from left to right, I'd have to go down 2 and over 1, which would be a slope of negative 2. So this would be negative 2, absolute value of x plus 2, and then in the back, I also have a plus 2 for my k value. Right there. So there's my nice absolute value portion of this. Wasn't the only thing there, but that was the big chunk. That was going to take 2 pieces of that graph off of here for me. So now my focus is on this. And I'm going to use a line to represent that. My hope is maybe it's as easy as y equals mx plus b. I mean, if I know what the intercept is and I can find the slope, then I can do that. And I can see the intercept. It's right here. The y-intercept is at negative 2. So we've got minus 2 for x greater than 0. And again, what was important was one of them got the equals bar. It wouldn't matter if you had moved that down here to the blue or not. They have to meet. And then for the slope, let's see if I can find a couple of really nice grid points. Yep. Those 2 look really good. So from left to right, I'd have to go up 3 and over 1. Done. So all of those things are things that you've done in Algebra 2 before. I haven't done them for a while. Might be a little rusty, but we've done them before. And it doesn't always have to be f of x. You can name it g of x, h of x. For some reason, that's the part of the alphabet that we tend to stick around, but you can actually use any letter you want. Should be lowercase, though. Uppercase letters in math usually mean there's something more going on behind the scenes that we need to know about. There's more to the formula. So now this one says, and I really like this one, this is one of the 12 basic functions. We just wrote it as a piecewise. Which one would it be? So it says identifying a piecewise defined function, which of the 12 basic functions has that for its piecewise? So if x is greater than or equal to 0, and you put in x, you just get exactly x right back. But if x is less than 0, you put a number in and you get the opposite back. Anybody think of it right away? Take a quick look at all the functions on your worksheet. So this is saying as we go to the right forever, we're just going to get the same number back. So that should go through 1, 1, 2, 2, 3, 3, 4, 4. But the left portion of this graph should give you the opposite. If you put in 2, you get negative 2. You put in 3, you get negative 3. Tristan, did you find it? That's what it is. And this is actually a really big one. Here's why. In calculus, you cannot do the things you need to do by just using f of x equals the absolute value of x. So what you have to do is you have to break it up into those 2 separate pieces so that you can do the differentiation that you need to do with those graphs. So knowing what is it when we break it apart is an important part of calculus. We have to do that quite a bit for the interesting functions. Example 7 says, using basic functions from this section, Let's put the arrows on there. We mean for it to be arrows. Using basic functions from this section, construct a piecewise definition for the function whose graph is shown in figure 1.52. Would it be continuous? Okay, do you see the changeover? Pretty obvious, right? At 0, something's happening, right? So f of x equals, and I'll just put for x less than or equal to 0 and x greater than 0. Again, it wouldn't matter because they do meet. It wouldn't matter which one of those gets the equals bar, but you just have to pick one. All right, so take a look at just the left side of that graph. Do you recognize it? Josiah, what did you see? Oh, careful. I think you just set it backwards. Yeah, squaring function, x squared. Now, we recognize the right side. Savannah, did you find it? That one's the square root, right. There it is. So again, these are things that you've done some work with in the past. These are not things that you haven't seen before. So it really does try to keep it to concepts that you've spent some time with in Algebra 2. Notice the basic questions about which ones are even, which are odd. Yeah, we'll throw cosine and sine and the logistic function and the greatest integer function in there. But generally for this stuff, we want something you could actually write, something that you know how to do. This one, interesting. Oops, there was a second part to this. I was telling myself while I was going through this, don't forget there was a second part. Is this something that we could draw without lifting our pen or pencil? Continuous. It is continuous. There's no breaks, there's no jumps, there's no time when we would have to lift our pencil up and say, okay, can't do this with just one swift move. Example 8, looking for a horizontal asymptote. Does this graph have a horizontal asymptote? Well, it kind of looks like it. But they told me it was y equals the natural log of x. All right? So I want to change that. Again, make it exponential. Oh. And because I'm right-handed, I like to have them that way when I make my little snail shell. So here comes my snail shell. So here's what they're really asking. Is there some y that we could not raise e to? Well, let's see. E is above the natural logarithm button, so second e to the, whoops, apparently it didn't grab my second. There we go. E to the 10th. Still going to get an x value. E to the 45th. Still able to do it. E to the 1000. Does it say that there's no such number? It just says this poor little machine can't give you that big a number. But it's still out there. I mean, we know that. So we get to the reasoning of, no, there isn't a y value that's suddenly going to be the very top of this. The numbers are just, the x values are just going to keep getting bigger. The calculator didn't say, can't do this. It said, you know, this calculating machine is not, you know, built to give you numbers that size. So, does it have a horizontal asymptote? No. It does keep going up. In this little screen, it kind of looks like, yeah, it flattens out, it doesn't go anywhere, but we know we can continue to do those y's. And this is why I said this one is dangerous. Look at how it looks like it stops, but it doesn't. It also goes down forever. And that can be a little trickster when people get to the test and we ask something about natural log. It's graph or error. It doesn't show you what's happening fully with that graph. Number 9. This one is the analyze. We have time. Do you want to finish it up? Because then you wouldn't have to watch a video tomorrow. Is that all right? Okay, let's do this. So this one is our absolute value graph. Give you like an extra day to do stuff, right? Domain. Can you think of any numbers that we can't find the absolute value of? Going right and left forever. Oh, but range. There's a whole lot of y values we're never going to use, aren't there? Yeah. Starts here at 0 for the y's and goes up forever. There we go. Is this something you could draw without having to lift your pen? It's continuous. Now, the decreasing, increasing, and constant, remember, is always left to right. So as we would read the graph, oh, well, my pen, my marker, would definitely be going down on the left-hand side. So negative infinity to 0, and with decreasing, increasing, and constant intervals, never use the square brackets. And then from there, it's increasing. Zero to infinity. We don't get any constant. Now, if this is a test, you want to put none. Here's why. I don't want to think you just forgot it. I want to know that you looked at it and said, no, there's no flat horizontal pieces to this. It's just not going to be constant. It's not going to be. Symmetry, remember, we only have 3 options. Even, odd, or neither. So which should we put for this one? Even. Does it have a local minimum or a local max? It does. Which does it have? A minimum, right? All right, so local minimum of 0 at, what's the x value where it's 0? 0. That also is the absolute minimum. We wouldn't have you write that down. Usually it just asks for the local mins and maxes. Does it have a maximum? Arrows show us it's going forever, right? So that's a none. Is it bounded? I wouldn't take off if you put bounded below. I wouldn't, because it is. It's bounded below, but it's just not bounded because the arrows are going up forever. But if you put bounded below, I would be okay. It's actually a little more specific than they really want, but bounded below is good. And then horizontal asymptotes, vertical asymptotes. See any? Does it have any division, any even roots when we talk about absolute value? So those are both none. And now we have to talk about end behavior, and that means we have to write that limit notation. So limit as x approaches negative infinity, did they call it f of x? Yes. F of x equals limit as x approaches positive infinity for f of x equals. So this one says, as we go to the left forever, if you had to only draw the left side of this graph, would it be going up or down? Is it going up? Yeah, so this would be infinity. Only drawing the right side of this graph, where's it going? Infinity again, right, because it's still going up. Both directions it's going up. We just analyzed one of those 12 basic functions. And you didn't have to look back at your white worksheet from yesterday. It's like, well, that's what absolute value looks like. Yeah, that's what I use. That's how I go through and do the analysis. So again, on the test, you just want to think, can I get a picture of the graph in my head? And go from there. And that's because, again, things like y equals the natural log of x, there's that graph or error piece. You don't want that. You want, hey, this is what I know the math tells me about this graph. Well, that was fantastic. Because there's day 1, and there's day 2, and you won't have to watch a video tomorrow. So I know we had 2 days set for the review. That's the Thursday and Friday, but if you wanted to, get a little head start on those, finish all this up in one day, totally up to you. Schedule it however you have time for it, knowing that we will be taking the test on Monday. Yeah, Monday. Well, you won't. You guys will be here on Tuesday for your test.